Integers. So far we are conversant with only two types of numbers, namely natural numbers and whole numbers. In this chapter, we shall extend our number system from whole numbers to integers. We shall discuss the representation of integers on a number line, operations on integers and their properties. Introduction to integers. We know that in numbers, when a smaller whole number is subtracted from a larger one, we get a whole number. But what about 3 minus 5, 5 minus 8, 11 minus 16, etc.? Clearly, there are no whole numbers to represent them. So, there is a need to extend our whole number system so as to contain numbers to represent the above differences. Corresponding to natural numbers 1, 2, 3, 4, 5, 6, we introduce new numbers denoted by minus 1, 2, 3, 4, 5, 6 called minus 1, minus 2, minus 3, minus 4, minus 5, 6 respectively, such that 1 plus minus 1 equals 0, 2 plus minus 2 equals 0, 3 plus minus 3 equals 0, and so on. We say that minus 1 and 1, minus 2 and 2, minus 3 and 3 are the opposites of each other, and so on. Thus, our new collection together with whole numbers becomes minus 3, minus 2, minus 1, 0, 1, 2, 3. These numbers are called integers. Positive integers. The numbers 1, 2, 3, 4, 5, 6, etc. are called positive integers. Clearly, the positive integers are the same as natural numbers. We denote positive integers 5 plus 1, 2, 3, 4, 5, 6, etc. or simply by 1, 2, 3, 4, 5, 6, etc. respectively. Negative integers. The numbers minus 1, 2, 3, 4, 5, 6, etc. are called negative integers. Zero integer. Zero is an integer which is neither positive nor negative. Remarks. 1. The numbers 0, 1, 2, 3, 4, 5, 6 are known as non-negative integers. The numbers 0, minus 1, 2, 3, 4, 5, 6 are known as non-positive integers. Application of integers in everyday situations. As we studied above, minus 1 and 1 are the opposites of each other. In general, we may say that negative and positive integers are the opposites of each other. So, they can very well represent real-life situations wherein we need to quantify opposite qualities. Examples. 1. Height and depth. We know that the heights and depths of places are measured as distances above and below the sea level respectively. Clearly, the sea level is treated as zero level. We shall represent 1. A height of 5 km above sea level as plus 5 km or simply 5 km. 2. A depth of 5 km below sea level as 5 km. Mount Everest is the highest point on the earth above sea level with an elevation of 8848 meters. Challenger Deep at the bottom of the Mariana Trench in the Pacific Ocean is the deepest known point with an elevation of minus 11034 meters. 2. Temperature. Temperature is a measure of the degree of hotness or coldness of a body. A thermometer is a device used to measure the temperature. Do you know that the freezing point of water is 0 degrees Celsius? At a temperature of 0 degrees Celsius of lower, water exists in solid form as ice, while at a temperature above 0 degrees Celsius, it exists as liquid water. We shall represent a temperature of 15 degrees Celsius above the freezing point of water as plus 15 degrees Celsius or simply 15 degrees Celsius. 2. 15 degrees Celsius below the freezing point of water as minus 15 degrees Celsius. As the temperature lowers, it gets colder. As the temperature rises, it gets warmer. Thus, minus 15 degrees Celsius is colder than minus 10 degrees Celsius. 15 degrees Celsius is hotter than 10 degrees Celsius. Death Valley in California is the hottest place in the world with temperature as high as plus 57 degrees Celsius. Vostok Station in Antarctica is the coldest place in the world with temperature as low as 89 degrees Celsius. 3. High-rise buildings with basements. Nowadays, in big cities, multi-storied buildings are being built as shopping malls with several floors above the ground level and a few floor basement under the ground. You must have noticed that the elevators in such buildings display the floor above the ground as 1, 2, 3 and the floors below the ground as minus 1, 2, 3. 4. Directions: north to south and east to west. 1. If moving 100 meter towards east from a fixed point O represents plus 100 meter, then moving 100 meter towards west from O represents minus 100 meter. 2. If moving 120 towards north from a fixed point 0 represents plus 120 meter, then moving 120 meter towards south from O represents 120 meter. 5. Credits and debits in banking and accounting. If we deposit money in our bank account, it is considered as credit, and if we not have spent money from our account, it is considered as debit. In short, we can infer that income is credited to our account and expenses are debited from our account. Thus, credits are denoted by positive integers and debits by negative integers. The total of all our credits and debits is our net bank account balance. A sample of the entries is as under: cash deposit plus 100, inward by check plus 150, cash withdrawal minus 50, outward clearing minus 80. Representation of integers on a number line. As shown below, every integer can be represented on a number line. Step 1. Draw a straight line and mark a point on it, almost in the middle of it, and call it 0. Step 2. Set off equal distances on the right as well as on the left of O. Step 3. On the right hand side of O, label the points of division as 1, 2, 3, 4, 5, 6, etc. While on the left hand side of O, label these points as minus 1, 2, 3, 4, 5, 6 as shown below. The arrows at the two ends on the number line indicate that the line extends infinitely in both the directions. Comparison of integers. If we represent two integers on a number line, then the integer occurring on the right is greater than the occurring on the left. Example. Look at the examples given below. 1. 5 greater than 2, since 5 is on the right on 2. 3 greater than 0, since 3 is on the right of 0. Minus 1 greater than minus 2, since minus 1 is on the right of minus 2. Minus 2 is greater than minus 6, since minus 2 is on the right of minus 6. If we represent two integers on a number line, clearly the smaller integer lies on the left of the larger integer. Look at the examples given below. Minus 5 lesser minus 2, since 5 is on the left of 2. Minus 3 equals minus 0, since minus 3 is on the left of minus 0. Minus 2 lesser 1, since minus 2 is on the left of 1. Let a and b be any two integers, then a is greater than b, a lesser than minus b. A lesser than b, minus a is greater than minus b. In general, we have the following results. 0 greater every positive integer, since 0 is to the left of every positive integer. 0 greater than, since 0 is to the right of every negative integer. Every positive integer is greater than every negative integer. A greater than B minus A is lesser than minus B. A lesser than B minus A is greater than minus B. Absolute value of an integer. The absolute value of an integer is the numerical value of the integer regardless of its sign. We denote the absolute value of an integer a by a, called the modulus of a. Thus, a equal to a if a is a positive integer or 0, minus a if a is a negative integer. Operations on integers. Addition on integers. We have learned how to add two whole numbers on the number line. We shall extend the number system method from addition of integers using the number line. Adding minus 3 to the number means moving 3 steps to the left of a number. Adding 2 to a number means moving 2 steps to the left of the number, and so on. Add plus 7 and minus 4 on the number line. On a number line, we start from 0 and move 7 steps to the right to reach a point A. Now, starting from A, we move 4 steps to the left to reach a point B as shown below. And B represents the integer 3. Thus, 7 plus minus 4 equals 3. Rules for addition on integers. Rule 1. If two positive integers or two negative integers are added, we add their values regardless of their signs and give the sum their common sign. 2. To add a positive and a negative integer, we find the difference of their absolute values and put the sign of addend having greater absolute value. Properties of addition of integers. Closure property of addition. The sum of two integers is always an integer. Thus, if 2 is the greater having integers, thus a minus b is also an integer. Commutative law of addition. Associative law of addition. If a, b, and c are any three integers, then a divided by b plus c equals a plus b plus c. Existence of additive identity. For every integer a, we have a plus 0 equals 0 plus a equals a. 0 is the additive identity in integers. Examples: 8 plus 0 equals 0 plus 8 equals 8. Minus 6 plus 0 equals 0 plus minus 6 equals minus 6. Existence of additive inverse. For every integer a, there exists an integer minus a such that a plus minus a equals minus a plus a equals 0. Here, a and minus a are called additive inverse of each other. Remark: a and minus a are called additive inverse or opposite or negative of each other. Successor of an integer. The successor of an integer a is a plus 1. The rules for addition on integers which we have just studied compiled by Brahmagupta in his work Brahmasput Siddhanta, dating back to around 630 CE as under. 1. The sum of two positives is positive. Example: 3 plus 5 equals 8. 2. The sum of two negatives is negative. To add two negatives, add the numbers without the signs and then place a minus sign to obtain the result. 3. To add a positive number and a negative number, subtract the smaller number without the sign from the greater number without the sign and place the sign of the greater number to obtain the result. 4. The sum of a number and its inverse is 0. 5. the sum of any number and 0 is the same number. From the above, what would you say about the following? We know that when the addends are of the same sign, the sum also carries the same sign. But when addends are of different signs, the sum carries the sign or the addend with a greater value. So we have positive plus positive equals positive, negative plus negative equals negative, positive plus negative equals positive or negative, negative plus positive equals positive or negative. Consider another example. The string shown below has a total of 100 tickets arranged in a particular pattern. Can you find the value of the string? Observe the string and its pattern carefully. Clearly, even every 5 beats have 3 plus and 2 minus. Thus, out of 100 feet, 60 are plus and 40 are minus. Required value 60 plus 40 equals 20. Subtraction on integers. For any two integers a and b, we define a minus b plus a plus minus b equals a plus additive inverse of b. Two useful result equals 1. A minus b equals a plus minus b. 2. A minus minus b equals to a plus b. We have minus 10 plus a plus b plus 4. A plus b equals plus 4 minus minus 10 equals plus 4 plus 10 plus 14. Thus, which of the above grids can be filled in multiple ways? Question. Is that question? What could be the same way? That is there any grid above which can be filled in on one and only one way? Which one? So this answer is also. So AB can be 113, 2, 12, 3, 11, 4, 10. Let's take AB as 311. Then A equals 3 and B equals 11. Now B plus 5 plus E equals 4. 11 plus minus 5 plus E equals 2 plus 4. 6 plus E equals 2 plus 4. E equals to plus 4 minus 6 equals minus 2. Thus we have the final grid as. You will agree that if we take different values of A, B, we can fill the grid in multiple ways. Grid 2. We have 6 plus 8 plus A equals minus 2. 14 plus A equals minus 2. A equals to minus 2 minus 14 equals to minus 16. Now A plus 5 plus B equals minus 2. So we obtain the final grid as this picture. Here we obtain a unique solution and this grid cannot be filled in any other way. Grid 3. Try and fill grid 3 in the same manner as we did for grid 1. You will find that in this case also there exist multiple solutions. A. Grid 1 and grid 3 can be filled in multiple ways. This is because along each border we are given the sum of 3 addends and the value of only one addend. So there are many possible pairs for the values for remaining 2 addends. B. Grid 2 can be filled in one and only one way because along border 1 we can given the sum of 3 addends and the values of 2 addends, so there will be a unique value of the third addend. The same process continues along with the borders too. The rules for subtraction on integers which we have just studied were compiled by Brahmagupta in his work Brahmasputta Siddhanta dating back to around 630 CE as under. 1. If a smaller positive is subtracted from a large positive, the result is positive. 2. If a larger positive is subtracted from a smaller positive, the result is negative. 3. Subtracting a negative number is the same as adding the corresponding positive number. 4. Subtracting a number from itself gives 0. 5. Subtracting 0 from a number gives the same number. Subtracting the number from a 0 gives the inverse of the number. From the above, what would you say about the following? Clearly, we have 1. From rules 1 and 2 above, we conclude that difference of two positive integers may be a positive or negative. So we have positive minus positive equals positive or negative. 2. Positive minus negative equals positive plus positive equals positive. 3. Negative minus positive equals negative plus negative equals negative. 4. Negative minus negative equals negative plus positive equals positive or negative. Multiplication of integers. 1. To find the product of two integers with unlike signs, we find the product of the values regardless of their signs and give a minus sign to the product. 2. To find the product of two integers with the same sign, we find the product of the values regardless of their signs and give a plus sign to the product. Properties of multiplication on integers. 1. Closure property to multiplication. The product of two integers is always an integer. Closure property, if a and b are integers, then a into b is always an integer. Associative law. For all integers a, b and c, we have a equals b into c equals a into b into c. Commutative law. For all integers a and b, we have a into b equals b to a. 4. Existence of multiplicative identity. It is an integer such that for every integer a, we have a into 1 equals 1 into a equals a. 1 is an integer multiplicative identity for integers. 5. For any integer a, we have a into 0 equals 0 into a equals a. Fill in the blank. 65 into 1. Solution 65. Minus 65 into 1, 65. Minus 23 into 0 equals 0. Division on integers. Solved examples. Divide minus 117 by 13. 168 by minus 12. 2 minus 72 by 16. Minus 25 2 by minus 21. We have minus 117 divided by 13 equals minus 9. 168 divided by minus 12 equals minus 14. 3. Minus 272 plus minus 16 equals to 17. Then minus 252 plus 21 equals to 12. Landmarks in the history of integers. 1. Zero and negative integers were first conquered of and used in Asia. The first known instances of the use of negative numbers occurred in the context of accounting. 2. In China's mathematical work, the 9 chapters of mathematical art by Zhuang Sanshu, which was completed by the 1st or 2nd century CE. Positive and negative numbers were represented using red rods and black rods respectively. 3. The concept of credit and debit was written about extensively by Kautilya in his book Arthashastra, wherein he recognized the possibility of a negative account balance also. 4. Negative numbers also found mention in the Bakshali manuscript, wherein a negative number was written using a special symbol placed after the number. 5. The first general treatment of positive numbers, negative numbers, and zero, all on an equal footing as equally valid numbers on which one can perform the basic operations of addition, subtraction, multiplication, and even division was given by Brahmagupta in his Brahmas Putha Siddhanta in the year 628 CE. 6. Brahmagupta was the first to describe zero as a number on an equal footing with positive numbers as well as with negative numbers. He was also the first to give explicit rules for performing arithmetic operations on all numbers, positive, negative, and zero, forming what is now called a ring. 7. However, it took many centuries for the rest of the world to adopt zero and negative numbers as numbers. 8. The name integer was first introduced in the year 1563 by Arthur Mott Holst from a Latin word meaning untouched. 9. The positive and negative numbers did not become a part of the number line until 1890 when Japanese mathematicians worked on it, but now they have become indispensable in global mathematics.